All right, folks. In this video, we are going to find the derivative of the natural log function. All right. So in other words, we're going to say let y equal natural log of x, and we're going to find that derivative. All right. So this is what section 3.6 is all about. What we're going to use to do this, the technique is we're going to use implicit differentiation, which we used in the previous section. All right. This is kind of fun. Implicit differentiation can be fun. This one in particular, it almost seems like we're not really doing any work. I mean, we're kind of like manipulating the system. So let's go ahead and see how this works out. Once we're all done, I want to look at the graph and show how the graph of the function and the derivative do match up and everything like that. Okay, so if I want to use implicit differentiation, the first thing I want to do though is natural log of x. I want to remember, natural log of x is log base e of x, right? That's all it means. So it's just a log function, but the base is e. And we've got a log property that if you take a base b, right, and raise it to log base b of x, then the answer to that is x, right? The answer to that is x, or the result of that. And the reason why that is the log is an exponent. All right, log base b of x is whatever particular exponent it would require that if you put on the base b, then the answer is x, right? That's what log base b of x means. It's the exponent that if you apply it to b, the answer is x. So that's what that log means. What are we doing here? We're applying that as an exponent to b, and so the result is x, right? So that's one of our, we call it the inverse properties, but that's true. And so since here we're dealing natural log is log base e, then if I take e and raise it to log base e of x, I end up with x. And so if I've got e raised to the natural log of x, which is what I'm going to do over here, that's going to turn into an x. Okay, so once we've established that, let's do that now. So what I want to do is, essentially I want to do this. Say e to the y is the same as e to the natural log of x. But I'm going to rewrite it so it looks a little bit neater. Let me give myself a little bit more space. So we're starting like this. Y equals natural log of x. And then what I want to go from there, the next line is then e to the y is the same as e raised to the natural log of x. Okay? And the reason why that works is if we're claiming that these two things are equal, then if we use them as exponents, they'll do the same thing. Right? They really mean the same thing. So e to the y is equal to e to the natural log of x, but we just argued that e to the natural log of x is really just x. So what I've got right now is e to the y is just equal to x. Okay, so now I want to take the derivative of both sides, or apply my differential operator d dx to both sides, and then that's going to require implicit differentiation on this side because I've got a function of y right there. All right, so let's do that. So I'll show that step happening. So here we've got this. So what I'm going to do is take the derivative with respect to x of the left-hand side, which is a function of y at this moment, e to the y. And so if e to the y is the same as x, then if I apply the differential operator to one side, I apply it to the other side and maintain my equality. So the derivative of x with respect to x. So that's what we're doing. Okay, the right-hand side of that is real nice, real easy. That's just equal to 1. All right. How can you argue that that's 1? Well, that's saying the derivative of the line, if you're thinking of the line y equals x, with a function f of x equals x, remember I've argued this, the slope of that line is constantly 1, so therefore its derivative is constantly 1. Also, since I sometimes talk about how this notation melds with fraction notation, right, and with you can kind of put the argument of that derivative up there. If you think of that as dx over dx, right, if that was a fraction, that would equal 1, and so as derivatives, that's 1. So our right-hand side is just 1. Can't get nicer than that. And what's happening over here? So what I'm doing is I'm taking the derivative of a function of y. So remember, the derivative with respect to x of a function of y means I better first take the derivative with respect to y. So I want to take the derivative of e to the y with respect to y, and then multiply that by the derivative of y with respect to x, right, to tie those two things together. So that's what I want to do right there. So the derivative of e to the y with respect to y, right, is another copy of e to the y. That's how e works. It reproduces itself. So the derivative of e to the y with respect to y is e to the y. And then what I'm multiplying that by is dy dx, right, which sometimes we like to call y prime. They mean the same thing, and it's a little bit more concise. So let's call that y prime. All right. So there we go. Just to clean that up under here, I think that was in the reflection right there. But derivative of with respect to y of e to the y is e to the y, and then multiply by that derivative of y with respect to x, which we're calling y prime, and so that's what we've got right there. All right. So where is this getting us? Where is this getting us? Because if you follow me to there, you might say, okay, but now, this looks like a mess. But we're actually almost done. We've got, let's say, 2 more steps to go. Let's think about what we started with, and so what we want to end up with. We're trying to find the derivative of the natural log, right? So here, y is the natural log. So that means we want to find the derivative of y, and the notation-wise of that, the derivative of y is y prime. So we found it, right? It appeared. We have to just isolate it right now. So to isolate that here, I'm multiplying on this side by e to the y. So we divide both sides by e to the y. All right, and so we found that derivative. Y prime is 1 over e to the y. Okay. So I said there were 2 more steps, right? Dividing by e to the y is one of them. But then now we started with the function of x, so we want our derivative to be a function of x, right? We don't want to define y prime in terms of its sort of parent function y. And so we just have to make a substitution. But where's that substitution? It's right here, right? E to the y is the same as x. That appeared in our work. So what does that mean? That means y prime is 1 over x. So I'll link them with an equal sign right there, and then maybe I'll clean it all up and put it up top. Okay. So really cool, actually, because that's like a basic function that we deal with all the time, and that came as the derivative of natural logs. All right. Kind of interesting, right? Because logs, natural logs, and the natural exponent e to the x exponential function, they're related. So we take the derivative of an exponential function and we get back an exponential function, right? However, here we take the derivative of a log and we kind of lose the logs and we just go back into 1 over x. All right, there we go. So let me write that up here. And then I want to just discuss then the graphs of these 2 things a little bit. At this point, instead of calling it y, let me just go ahead and call it f of x. All right, and so therefore I can call its derivative, f prime of x, is the reciprocal function 1 over x. Okay, if I wanted to write that in d notation also, just while I'm at it, the derivative with respect to x of natural log of x is 1 over x. Okay, so that last line I just wrote there means exactly the same as sort of the 2 preceding lines put together. But remember, here I have to tell you what f is, tell you what f prime is. Here I'm just saying the derivative of this function is this function. So a little bit more concise. Okay, let's just discuss the graphs of those things. Let's think about the domains of those functions for a second, because the domain of natural log of x is all positive numbers. We cannot take the log of 0, and we don't plug negatives into logs. And those relate back to the range of exponentials, range of exponential functions. So there, we've got that. The domain, so all positives. The domain of this, though, domain of 1 over x, is everything except 0, so including negatives. All right. So they're both undefined for 0, so that's helpful. So if you really want to be technical, you might restrict the domain of this thing by saying x must be positive, so put a little requirement on there. Don't worry too much about that. However, I'm gonna sort of generalize this to make another function that's real similar to this function f, whose domain actually is, whose derivative is 1 over x, and for all these numbers, including the negatives. So what could we do to that log so negatives become okay? So we'll get there in a second. So here, though, the domain of a log function is 0 to infinity. A log function looks like this, right? So as we get closer and closer to 0, it plummets down towards negative infinity. Log of any base of 1 is always 0, so that's this intercept right there. And after that, it keeps increasing, right? So it's a constantly increasing function, the natural log is, but it's sort of slowing down in its increasingness. In other words, you might say the slope of its tangent lines is getting more and more horizontal, right? And the slope of a horizontal line is 0, so that's that would be the relationship between the derivative would describe that relationship a little bit. All right, so let me sort of graph the derivative. And so again, since the domain of natural log of x is only positives, let me just graph 1 over x for just positive values, right? So 1 over x looks like something like this. All right, 1 divided by 1 is 1, right? So this passes through the point 1, 1. So let's think about this. This piece of this 1 over x function is always positive, meaning that when x is in this in this domain, right, for positive inputs, positive x values, then 1 over x is always positive. So the derivative here is always positive. So f prime greater than 0, right, for all x greater than 0. So that's speaking about the domain. But in other words, when x is positive on this side of my y-axis, the derivative is always positive, which means the original function is always increasing, meaning it's moving up as we move to the right, right? Because a positive derivative means the slopes of those tangent lines are positive. So that means f is increasing. Here I said for all x greater than 0, that's one way to say it, or you could say on the interval 0 to infinity, maybe another way of saying it. So f is increasing on the interval 0 infinity. In other words, our natural log is increasing on this interval, and that's its whole domain, so it's always increasing, right? So if somebody's asked you to, in pre-calc you study this function, in calculus if somebody says prove that function's always increasing, right? How do I know it never actually levels off or turns around and starts falling, right? How do I really know that? Use the derivative, right? Its derivative is always positive, so those tangent lines are always positive, which means the function must be increasing. So that's cool. What about though, so before we said it's increasing, but if I'm going to kind of miss the function with the tangent lines, but the tangent line looks kind of parallel to that, and then parallel to that, and then parallel to that. So they're always increasing, moving up, but they're getting more and more horizontal, right? And we said the slope of a horizontal line is 0, so that means the slope of these tangent lines is positive, but sort of shrinking, getting smaller and approaching 0. What's happening to this derivative graph as x approaches infinity, as we keep moving to the right? It's always positive, but it's getting smaller and smaller and approaching 0, right? So kind of cool. So this graph really does mimic the behavior of that one, or describe the behavior of that one. So that's cool. What is the equation of the tangent line right here at this intercept? All right, let me draw that tangent line right there at that intercept. What is the equation of that line? How would we figure that out? Well, I've got an x-coordinate and I've got a y-coordinate. And if I want to write the equation of a line, I will do it in purple because I don't know if the red shows up great, but I want to do y equals mx plus b. All right, so x is 1, right? Y, the y-coordinate is f of 1, you could say, right? So if I were dealing with function notation, I might say f of 1, which is the function value at 1. What's the slope? The slope is f prime of 1, right? So if x is 1, then the function value, the original function value, which is the natural log, tells me the y-coordinate. The derivative tells me the slope. And then, as usual, I got to figure out what this y-intercept is. It looks like it's going to be a negative number. If that slope is 1, it should probably give us -1, but let's solve for it. All right, so I've got that. So f of 1 is the y-coordinate right there, 0, which is natural log of 1, right? So we get 0, is equal to f prime of 1 is 1 over 1, which is 1, right? So that slope of that red line right there is 1. And then I've got times 1 and plus b. So 1 times 1 is 1. Subtract the 1 over, and we get b is equal to -1. All right, and so the equation of this line is y equals, my slope is 1, so I could write 1x minus 1, or just x minus 1. There we go. Right, so exploring the relationship between the graph of the derivative, comparing it to the original graph, noticing the behaviors, getting an equation of a tangent line. So typical exercises or applications that we might do once we've got a derivative. All right. So let me sort of extend this a little bit. Back to the idea of the domain. So one function you'll see a lot, and you'll use a lot in Calc 2, is the function, what if I had natural log of absolute value of x? Right? What happens if I wrap absolute value sign around that x in there? Well, what that means is the absolute value of 0 would give me 0, right? And log of 0 doesn't exist. So 0 is still problematic. However, now if I plug a negative number into this function, then the bars turn it into a positive number, right? So the bars take away any negativity, and then that positive number can get plugged into natural log, which means if I put absolute values around the x, I've expanded my domain. I've essentially doubled the size of it, right? Now I include all negative values. So there's my domain. Negative x values can now be plugged in, okay? What is that going to do? How is that going to sort of augment the graph, right? What else is going to appear? Well, for any positive x value, then the absolute value of the positive is itself. So for all these function values, it remains unchanged. And what happens is we essentially get a mirror image over here, right? Let's see that just by finding the x-intercept. So I claim if we get a mirror image, then the point -1, 0 should live there. So if I do f of -1, that's natural log of the absolute value of -1, right? But we know the absolute value of -1 is just +1. And natural log of +1, or natural log of 1, is 0, right? So we plug -1 into there, we still get 0. You can try some other points, or trust me that it's going to treat every negative number as the positive version of that number. And so that's going to create the reflection. So let me see if I can create this reflection. All right, looks something like that. So it's kind of encroaching on this graph over here, but that's okay. So I get this other piece. What can we say about that piece? Let's go back to the actually original piece. And so we talked about what happened when we moved to the right, that the slopes of these tangent lines were always increasing. So we had positive slopes, but they were, I'm sorry, I should say the tangent lines themselves are increasing, but the slopes were sort of shrinking, right? Getting more and more close to 0. As we move towards, as x moves towards 0, as we approach the y-axis here, the slopes of these tangent lines are always positive, but the tangent lines get steeper and steeper, meaning their slopes gets larger and larger. And so that's why as we approach 0, as x approaches 0 on this graph, we get larger and larger and larger, right? So these high function values are describing the high slopes that we get over there. Okay, what's going to happen as we do, so let's kind of, I'm going to forget that I know what the derivative is and kind of try to describe the behavior of what's happening over here. So if the slope of that red line was a 1, and I just took a mirror image, then that means the slope of that line should be -1, right? So that means if I plot, when x is -1, the slope of that tangent line is a -1, which means for my derivative, if x is -1, then the derivative should be -1. So that point should live on the derivative. What happens as I move this way? So all these tangent lines are going to have negative slopes, right? But as I move to the left now, they're sort of flattening out, right? Approaching 0. So that means as I move to the left on the derivative graph, I should stay in the negative portion. So I'm beneath this axis, but I'm getting closer and closer to 0. And as we get closer from this intercept towards the y-axis, they're negative, but they're getting steeper and steeper and steeper. So large negative numbers, which live down here, and so the graph should want to do that of its derivative, right? So that's just sort of using the reflection, using what we know about the behavior of these tangent lines to describe what should happen over here. And what's the graph of 1 over x look like for negative x values? It looks exactly like that, right? 1 over x has this piece that lives down here in quadrant 3. So that's cool because we had the little difference of domains right there, but if we consider this function, now whose domain is more inclusive, now it really matches up exactly 100% with this function as the derivative of this function. Okay, cool. We did all of that. Remember, we found the derivative using implicit differentiation, so powerful technique, good practice running through that. There we go.